Let's start. So today we're continuing on with chapter 4, and we're talking a little bit about mole to mole conversions using our formula. So looking at C2H4, let me just draw a picture of that. It doesn't have to be fully descriptive. It doesn't have to be a Lewis structure. We just want to know how many atoms of each element do we have. So looking at C2H4, in 1 mole of C2H4, how many moles of hydrogen do we have? How many hydrogens do we see?
4.
4, exactly right. So this is our first mole to mole ratio. Likewise, how many moles of carbon are there in 1 mole of C2H4? How many carbons do we see?
2.
2, exactly right, exactly right. So we can also generate a relationship between carbon and hydrogen. So how many moles of carbon do we have per how many moles of hydrogen? What's our ratio of carbon to hydrogen? And don't be shy to share your responses verbally or in the chat. What is our mole to mole ratio, looking at this formula C2H4, of the moles of carbon to the moles of hydrogen?
2 to 4.
Yep, exactly right. We have 2 moles of carbon, 2 carbon atoms per every 4 hydrogen atoms. I just want to emphasize once again, this mole to mole ratio can also be written as an atom to atom ratio. So we have 2 atoms of carbon per 4 atoms of hydrogen. Okay, so we were able to generate some mole to mole ratios, some conversion factors from our formula. Now, let's apply these conversion factors to calculate the moles of an element in a sample. So we're asked how many moles of carbon are in 5.5 moles of C2H4. And then the second question, we're asked how many moles of hydrogen are in a sample of C2H4 containing 3 moles of carbon. So I want everyone to take about 3 to 4 minutes on these examples, and I'd like you to complete these 2 unit conversions. If you need a reference guide for how to complete these calculations, I did a sample example on page 21 last class session. We're now focusing on the application of what we've learned last session, and this example will help us integrate the concepts and apply what we've learned. So let's take about 3 to 4 minutes, and I'd like you to answer questions A and B, calculating the moles of carbon in our sample and the moles of hydrogen in a sample, given the moles of our compound and given the moles of one of our elements. And don't be shy to share your responses verbally or in the chat. And if you have any questions as you attempt these examples, don't be shy to ask your questions verbally or in the chat. These kinds of problems are best learned by application, and I'd like to see some shared responses verbally in the chat for these 2 examples. Or if you're unsure, a question would be invaluable at advancing our discussion, and many questions that you have may be shared by your classmates. So let's keep, yeah. Mhm.
Sorry.
No, please
I,
go ahead.
I have a question. What you said earlier on the top of this page, it says that the moles of atoms and moles of molecules can also be written as 2 atoms and what else?
It can, so the mole to mole ratio can also be written
Uh,
as an atom to atom ratio.
Atom to
Um,
atom ratio.
yep.
Okay, thank you.
So the formula ratio provides a relationship between the moles of atoms of each element as well as the number of atoms of each element.
Got it. Thank you.
Mhm. So we're starting to see a few responses in the chat for these questions. Don't be shy to contribute your own responses. And it's wonderful to see students participating in the chat. And if there's any part I can clarify in these questions, don't be shy to ask. We'll discuss this example in about another minute. And you mainly want to have as much of your setup prepared as possible. So that way, when we go over the solution, you can compare your setup to the solution that I've proposed. But it's great to see a range of students participating in the chat, as it really helps me understand and it helps me see parts of this discussion that I can address further and parts that students feel confident about. Okay, so the notes are found under Canvas under week 7, week 8, or week 9, and they're labeled the chapter 4 notes. And this is on page 22 of the notes. So to discuss our solution for this question, I always like and I would highly recommend setting things up as a unit conversion map. We are starting with the moles of C2H4, and we are trying to calculate the moles of carbon. So as such, if we start with 5.5 moles of C2H4, we're going to need a conversion factor. If we're going to moles of carbon, we're going to need moles of carbon on top. To cancel moles of C2H4, we need moles of C2H4 on bottom. Looking at our formula, we have 2 moles of carbon per 1 mole of C2H4, and that gives us 11 moles of carbon. Does this first example make sense? Does this first example make sense? Any questions on this first example? Okay, so in this first case, we've converted from the moles of a compound to the moles of an element. This is very common, especially when we start to look at ionic compounds in solution. Now we're going to look at a conversion between the moles of one element in a compound and the moles of another element. So in this case, we're given the moles of carbon. This is what we're given, so that goes on the left, and we're trying to calculate the moles of hydrogen. Now that we have our scheme established, we're going to set up our unit conversion factor. So to go from moles of carbon to moles of hydrogen, we're going to need the moles of hydrogen on top and the moles of carbon on the bottom. Looking at our formula for C2H4, we see we have 4 moles of hydrogen per 2 moles of carbon. Our units cancel, and that in turn gives us 6.0 moles of hydrogen. Does this example make sense to everyone? Does this example on page 22 of the chapter 4 notes make sense to everyone? Any questions? Any questions on this example? Okay, so let's start to add a little bit of complexity here. The chemical formula, as we've discussed previously, is also a relationship between the molecules, the number of molecules, and the number of atoms of an element in those molecules. The chemical formula can also provide a relationship between the atoms of one element in a compound and the atoms of another element in that compound. So for example, in B2H6, not a very fun compound to work with because it's quite flammable, but nonetheless, it's interesting to consider. So looking at this formula, in one molecule of B2H6, so in one molecule of B2H6, how many atoms of hydrogen do we have? In one molecule of B2H6, how many atoms of hydrogen do we see?
6.
Yep, exactly right. So we have our atom to molecule ratio. Now let's look at this second example, and I'd like you to tell me from the same formula how many atoms of boron do we have per one molecule of B2H6? How many atoms of boron do we have?
2.
2, exactly right. And just like before, we can also develop an atom to atom ratio where we have 6 atoms of hydrogen per how many atoms of boron? Looking at our formula for B2H6, we have 6 atoms of hydrogen per how many atoms of boron?
2.
2, exactly right. Okay, so as we've just done, we can generate a series of atom to atom and atom to molecule ratios. This is on page 23 of our notes. Now what we can do is we can apply these atom to molecule and atom to atom ratios to convert between different units of measurement. So for example, we're asked how many atoms of boron are in a sample that contains 1.5 times 10 to the 20th molecules of B2H6. So we are trying to go from molecules of B2H6 to atoms of boron. Always write out your units. This map will keep your logic focused and will allow you to check your work. The more you map out your problem-solving process, not only the easier will it be for you, but the easier it is for me to assign partial credit when you provide work. So we have 1.5 times 10 to the 20th molecules of B2H6. Now, if we are converting to atoms of boron, how many atoms of boron do we have per molecule of B2H6? So looking at the formula, we have 2 atoms of boron. So then, punching this into our calculator, that in turn gives us, whoops, that's not the right pen width. There we go, 3.0 times 10 to the 20th atoms of boron. So the actual mechanics are identical to our mole-to-mole conversion examples. We're just using slightly different unit labels. Does this first example make sense?
Professor,
Yes.
when you get the answer, we go ahead and multiply like the 1.5 times 2? Or
Yep,
what?
exactly right. And 1.5 times 2 would give us 3. Does that make sense?
Got it. Yes, thank you.
Perfect. And just as a reminder, this ratio, because it's derived from counting, is an exact number. So it will never affect the significant figures in your final answer.
So Professor, going back to
Yes, please go ahead. I'm sorry. I think your audio cut out momentarily. Would you be able
Oh,
to
okay.
repeat?
Yes. Can you hear me?
Yes, I can.
Okay. On the page 22 on section B, when we multiply the 3.0 and the 2, obviously we get the 6.0 mole of hydrogen.
Yep.
But we don't do anything with the 4 on top?
Oh, we did, because 3.0 times 4 over 2 gives us 12 over 2, which gives us 6.
Okay, how do we multiply on our calculator 4 over 2? Just,
So what you would do is first you'd enter 3 into your calculator, then you'd
uh-huh,
hit the multiplication symbol,
uh-huh,
then you'd enter 4, then
uh-huh.
you'd hit the division symbol, and then you'd enter 2. And then you'd hit the equals.
Got it.
Does
Okay,
that
I
make sense?
had missed that step. Yes, thank you.
Mhm. No problem at all.
Appreciate it.
And of course, I can also, if there are more detailed examples that you'd like me to enter into the calculator, don't be shy to ask, and I can share my camera screen and show you how I'd enter it into my own calculator as well.
Thank you very much.
Yes, no problem at all. So let's look at this next example now. We're asked how many atoms of hydrogen are in a sample that contains 3.0 times 10 to the 19th atoms of boron. So in this case, we're going from the atoms of boron to the atoms of hydrogen. So if we have 3.0 times 10 to the 19th atoms of boron, this is why I encouraged you earlier on to be very specific when you talk about moles and atoms of what? The more specific you are, the easier it is for you to keep the units organized. Okay, so if we're going from atoms of boron to atoms of hydrogen, we need to put atoms of hydrogen on top. So atoms of hydrogen, how many atoms of hydrogen do we have per atoms of boron?
6.
Yep, we have 6 atoms of hydrogen per how many atoms of boron?
2.
2. So from this ratio, just to show how we'd enter this into the calculator, we have 3.0 EE19. Then we're going to hit the multiplication symbol, then 6, then the division symbol, followed by 2. And that in turn gives us 9.0 times 10 to the 19th atoms of hydrogen. Does this example make sense?
That
Where do
just,
we get, sorry,
Please go ahead. Whoever wants to go first, I'll be happy to answer both questions.
where do
Can I
we
just,
get, oh, I'm sorry,
go
go
for it.
ahead. Go ahead, I'll wait.
Okay. Can I just times 3?
Yes, you can. You can. Mhm. That would be more than okay. That would give you the same result, because
Where,
this 6 over 2 is just the same as 3.
and
Mhm.
where do we get the 6 over 2 from? From the problem? Where's that at?
So the 6 over 2, which is our atom to atom ratio, is obtained from our formula. If we look at our atoms of hydrogen, what is how many hydrogen atoms do we have?
6,
Yep. And how many boron atoms do we have?
2.
2. So we have 6.
Okay, so that's just a general formula that we use when we're using atoms?
Yes. So in general, in these problems, you'll be given the formula of your compound, and you'll be asked to use a unit conversion used from that formula. So given that we have a sample of B2H6, we're able to convert from the atoms of boron to the atoms of hydrogen using this formula.
Okay, got it.
Does
Thank
that
you.
make sense?
Yes, thank you.
Perfect. So let's now try to apply what we've learned to the following example. And before we let you loose to work on some problems, let's establish some atom to atom and atom to molecule ratio. So in S3Cl5, trisulfur pentachloride, how many atoms of sulfur do we have per molecule of S3Cl5?
3.
Yep, exactly right. Now let's look at our other element in this compound and how many atoms of chlorine do we have per molecule of S3Cl5?
5.
5, exactly right. We're just reading off our subscripts. Now, in addition to an atom to molecule ratio, we can also generate an atom to atom ratio. So from our formula, how many atoms of sulfur do we have per how many atoms of chlorine? What's our atom to atom ratio?
3 to 5.
Yep, exactly right. We have 3 atoms of sulfur per 5 atoms of chlorine. Okay, perfect. So now that we have our atom to atom and atom to molecule ratios established, we're next able to answer the question, how many atoms of sulfur are in a sample that contains 2.2 times 10 to the 18th molecules of trisulfur pentachloride? So in this case, we're starting off, let's just look at our units. We're starting off with molecules of trisulfur pentachloride, and we're trying to convert to atoms of sulfur. I'd like you to take what we've covered in the previous examples, and I'd like you to work on the following 2 problems that apply these formula ratio unit conversions. So let's take about 3 to 4 minutes to work on these 2 examples, and then we'll come together as a group to discuss. Don't be shy to share your responses verbally or in the chat. And of course, if you have any questions at all, don't be shy to share them and ask them verbally or in the chat. And you can also send your proposed responses and questions as a private message, though I prefer the class-wide discussion, so that way students can see how other students are approaching the problem and start to contribute to a broader class discussion. So let's spend about 3 to 4 minutes, and then we'll discuss these 2 examples. And it's great to see a pool of responses, and it's also encouraging to see that students are getting a little more efficient in their calculations the more examples in this theme we're working on. But don't worry. Keep working through these problems and really don't be shy to share your responses. I really like hearing from everyone in the class because it helps me structure my feedback and structure how I provide these solutions in a way to address any questions and common issues that I observe in different student solutions. So let's keep working on this example and we'll discuss in about 2 to 3 minutes. And it's great to see a pool of responses in the chat. Let's keep working through these examples and let's try to get a few more responses from other students. And we'll discuss in about another minute to a minute and a half. Okay, so let's discuss this example. Thank you everyone for sharing your responses. And now let's talk about the instructor solution so we can have something for our note set. Thankfully, most of the approaches taken in the chat are exactly the same way I'd solve this problem if I was given this problem as a fresh example. So first, we are starting off with the molecules of trisulfur pentachloride, and we're trying to calculate the atoms of sulfur. I know it seems silly to write this conversion map every single time, but it keeps your logic organized. And in later problems, this organizational framework will be invaluable. So, starting off, we have 2.2 times 10 to the 18th molecules of S3Cl5 or trisulfur pentachloride. And if we are trying to convert to atoms of sulfur, how many atoms of sulfur do we have per molecule of trisulfur pentachloride? How many atoms of sulfur do we have?
3.
3. Yep, so punching this into our calculator, that gives us 6.6 times 10 to the 18th atoms of sulfur. Does this example make sense to everyone? Does this example make sense? Okay, so let's look at our second case. We're asked how many atoms of chlorine are in a sample of S3Cl5 that contains 7.3 times 10 to the 12th atoms of sulfur. So in this case, we're trying to convert between atoms of sulfur to atoms of chlorine. Okay, given that we have 7.3 times 10 to the 12th atoms of sulfur, my question to all of you is, how many atoms of chlorine do we have per how many atoms of sulfur? What's our atom to atom ratio in S3Cl5?
5 to 3.
Yep, we have 5 atoms of chlorine to 3 atoms of sulfur. And punching this into our calculator, that in turn gives us 12.16 times 10 to the 12th, which we round to 1.2 times 10 to the 13th atoms of chlorine. I wanted to show everyone those steps just to make sure that when you write your final answer in scientific notation, that you make sure that your power of 10 is correct. Does this make sense to everyone? Does this make sense to everyone? Okay, so let's start to combine what we've learned together and handle some more complicated conversions. So in this case, we're dealing with a mass to mole conversion, which again uses our molar mass, and then we're following this up with a molecule to atoms conversion, which utilizes our formula ratio. So let's look at an example of this. So we're asked to calculate the moles of chlorine in 16.0 grams of carbon tetrachloride. So we're given the grams of carbon tetrachloride and we're asked to calculate the moles of chlorine. Now, where do we get the moles of an element from? If we know that we have a compound, what units should we place as our intermediate stepping stone? Where do we get the moles of an element from? If we have the mass of a compound, what unit are we going through?
Mole per gram.
Yep, so we're going to go through the moles of our compound, which is carbon tetrachloride. Exactly right. Does this scheme make sense to everyone? Does this conversion map make sense? We're taking the two concepts that we've covered previously, mass to mole conversions and formula ratio conversions, and we're linking them together into a multi-step conversion. Okay, so I'm going to draw a picture of carbon tetrachloride. It's a pretty fun molecule. It's non-polar, and it's a useful solvent. Anyway, if we have 16.0 grams of carbon tetrachloride, let's now execute on this problem-solving map. We're asked to go from grams of carbon tetrachloride to moles, and in 1 mole of carbon tetrachloride, we have how many grams? Well, we have the tools to calculate that, now don't we? We can calculate the mass per mole of carbon tetrachloride. That is a straightforward molar mass calculation. And looking at the molar mass of carbon tetrachloride, we take the mass of carbon plus the mass of chlorine times the number of chlorine atoms. And that gives us, for carbon tetrachloride, 12.01 plus 35.45 times 4. And that gives us a molar mass of 153.81 gram per mole of carbon tetrachloride. So we just fill that in right here. Does this molar mass calculation look familiar to everyone? Does this molar mass calculation look familiar?
Yes.
Okay, perfect. So now that we've completed our first step, which is the mass to mole conversion, we're now going to do a mole to mole conversion using our formula ratio. So if we're going from moles of carbon tetrachloride to moles of chlorine, we have to answer the question, how many moles of chlorine do we have per mole of carbon tetrachloride? What's our mole to mole ratio? How many chlorines do we see?
4 to 1.
Yep, 4 to 1. We see 4 moles of chlorine per 1 mole of carbon tetrachloride. So let's punch this into our calculator. We hit 16 divided by 153.81 times 4. And that in turn gives us 0.416 moles of chlorine. Does this example make sense? We've seen both of the parts to solving this problem. We're just now taking them together and applying both of those parts. Any questions on this first example? Well, let's add some more data points. Let's add some more solved examples to our list to help us integrate what we've learned. So we're asked what mass of C2H2 contains 4 moles of carbon. Okay, so we're given the moles of carbon and we're asked to calculate the grams of C2H2. Now, how do we calculate mass of a compound? What units do we go through? What intermediate units?
Gram.
Yep. Sure. So we're trying to calculate the mass of C2H2. And where do we get the mass from? How do we calculate the mass? What units do we start with if I want to find the mass of a compound?
Gram per mole.
Yep. So we're going to use our molar mass. Yep. Which has the form gram per mole. And if we're trying to calculate grams, what units should we start from? if we're trying to get to grams, what units should we start from if we're trying to get the grams of C2H2 using our molar mass? What's our intermediate stepping stone?
Mole per gram.
Exactly. So we're going to need the moles of C2H2. Okay, so now that we have our solution map, we can execute on this solution map. We know that we have 4.0 moles of carbon. And now looking at the formula for C2H2, if this sample of C2H2 has 4 moles of carbon, how many moles of C2H2 are found per mole of carbon that we isolate from our sample? What's our mole to mole ratio looking at C2H2?
One, two, two.
Yep, in 1 mole of C2H2, we have 2 moles of carbon. Okay, now that we have the moles of C2H2 clearly established, we next can convert to the grams. So how many grams of C2H2 are found in 1 mole of C2H2? That requires a molar mass calculation. So we take 12.01 gram per mole of carbon. We have 2 carbon atoms. We have 1.00 gram per mole of hydrogen. We have 2 hydrogen atoms. And that in turn gives us 26.02 gram per mole of C2H2. I would encourage you to practice molar mass calculations rather than just looking up the molar mass, as a central part of a lot of these problems is getting you used to finding the data from your periodic table and using it to calculate meaningful values. So now that we have our scheme set up from our solution map, we filled in our conversion factors, now we just execute. So we take 4 times 1 divided by 2 times 26. And that in turn gives us a mass of 52 grams of C2H2, which is acetylene. Does this make sense? Any questions on this example? Any comments? How's everyone feeling on this? We are just linking together the 2 different types of unit conversions that we've discussed in this class, and now we're applying them together to do a multi-step unit conversion. So, to help tease out any potential concerns or questions that you have, I'd like you to work on the following examples. We're asked to calculate what mass of nitrogen triiodide contains 5 grams of iodine and how many moles of sulfur are in 32 grams of hydrogen sulfide. And now you may say, wait a minute, I don't see the formulas here. Well, from the name, we can figure out the formulas, right? We know from nomenclature how to calculate and determine the formula. So to show that this is it's not impossible, I'd like everyone in the class, before we break out into groups, I'd like us all to work and let's try to figure out the formula for nitrogen triiodide. What would the formula for nitrogen triiodide be? Ni3, exactly right. Nitrogen, this is a covalent compound. Triiodide, tri means 3. So we have a formula of Ni3. Perfect. Okay. Next, we're asked to calculate the moles of sulfur in 32 grams of hydrogen sulfide. Would someone like to provide us the formula for hydrogen sulfide? Would someone like to provide us the formula for?
H2S.
Yep, exactly right. Hydrogen sulfide, this is the covalent name. So in order to get the formula, we know for a binary acid in its molecular form, we write the charge of each of our two quote unquote ions, even though it's not an ionic compound, the formula is solved like an ionic compound. We then cross our charges, and that gives us H2S. So now that we have both of the formulas established, I'd like you to take about 4 to 5 minutes, and I'd like you to work on these two multi-step unit conversions in which you're asked to convert between the mass of a compound and the mass of an element, in which you're asked to convert between the mass of a compound and the moles of an element. So let's take about 4 to 5 minutes to work on this example. If you have any questions, don't be shy to ask it verbally or in the chat via public or private chat. And don't be shy to share your proposed responses in the chat or verbally. And if you're stuck, really do not hesitate to ask a question. And of course, as we're working through these problems over the next 4 to 5 minutes, if you have any questions or if you'd like a little bit more time, don't be shy to let me know.
Professor, for the question 1, since is gram to gram, do we need to have any intermediate mole or no?
You would need to go through moles
Even if it's like gram to gram?
Because there's no easy way to go directly from the grams of an element to the grams of that compound that we know right now. You could use mass percentage, and we'll talk about that later on in this chapter. But you're going to likely have to go through moles. Does that answer your question?
Yes, yes, thank you.
Perfect. So let's keep working through this example, and we'll discuss momentarily. And don't be shy to propose your responses. Verbally or in the chat. And if you have any questions, don't be shy to ask it verbally or in the chat. And we'll discuss this example in about another 4 minutes. These are the types of examples that I'd like to place on exams. So you want to be comfortable with these examples in the notes. And if there are any questions, don't be shy to ask. And it's great to see students sharing their responses. And if you have a proposed solution that you're unsure about, you can also take a photo and share the photo in the chat, and I'd be happy to look it over and provide feedback. You can also write out your proposed solution using the annotate feature in Canvas. I know as the low-tech option, sharing your response in the chat is also a great way of giving me a sense of how everyone's progressing through the material. And let's keep working on this example, and we'll discuss in about another 2.5 minutes. It's great to see that students are engaging with these problems and are willing to share their responses with the chat. And if you're stuck on a part, you can share where you're stuck, either publicly or privately, and I'd be happy to provide feedback to help you get through the problem. And let's try to continue working on these examples, and don't be shy to share your proposed responses in the chat. And even if they're different from your classmates, that's okay. It adds to the pool in our class discussion, and it allows us to flesh out our discussion and potentially address both different approaches to solving the problems and common stumbling blocks when encountering and working through these problems. So we'll discuss this example in another 1.5 minutes. I'd like to see a few other shared responses in the chat or verbally, or at least a question, just so that way when we go through the solution, I can make sure to address the questions that you have. Okay, so let's discuss. We're asked to calculate what mass of nitrogen triiodide contains 5 grams of iodine. So we're given the grams of iodine, and we're asked to calculate the grams of nitrogen triiodide. Now, how do we relate an element and a molecule? How do we relate the amount of atoms of an element and the number of molecules? What units?
Do we use the Avogadro number?
Um,
Atoms?
So you can, though it would add more steps. If we wanted to relate the amount of an element in a compound to the amount of a compound, what intermediate units are we going to go through?
Mole.
Moles, exactly right. So we're going to go from grams of iodine to moles of iodine. And then from moles of iodine, we can go to the moles of nitrogen triiodide. The way to relate the element in a compound to the moles of a compound, or to the amount of a compound, is using your mole to mole ratio derived from your formula. So the formula ratio provides a relationship between the moles of an element and the moles of a compound. And this in turn also allows us to relate the mass of an element to the mass of a compound. Does that make sense? Okay, so now that we have our conversion map established, we're going to start off with our mass of iodine, and we're trying to go from the mass of iodine to the moles of iodine. And to accomplish that, we're going to need our molar mass. So in 1 mole of iodine, we have 126 grams of iodine. Next, we're going to go from the moles of iodine to the moles of nitrogen triiodide. So in this case, my question to all of you is, how many moles of nitrogen triiodide do I have per mole of iodine? What is our mole to mole ratio?
1, 2, 3.
Yep, we have 1 mole of nitrogen triiodide for every 3 moles of iodine present in that sample. Finally, we're going to go from the moles of nitrogen triiodide to the grams. And to do that, we're going to use our molar mass and figure out how many grams of nitrogen triiodide per mole of nitrogen triiodide. So to calculate the molar mass for nitrogen, we have 14.01 gram per mole of nitrogen. We have 1 nitrogen atom. We have 126 gram per mole of iodine, and we have 3 iodine atoms. So punching this into our calculator, that in turn gives us 392 gram per mole of nitrogen triiodide. Okay, now that we have all of our conversion factors filled in, all we have to do is just execute. So we take 5.0 over 126 divided by 3 times 392. That in turn gives us 5.185 grams of nitrogen triiodide that we round to 2 sig figs, which is 5.2 grams of nitrogen triiodide. Does this make sense to everyone?
Professor,
Yes. Please go ahead.
Is that the mass of the iodine on the 126?
Yes.
Okay.
Does that make sense? So we're converting from the grams of iodine to the moles of iodine by dividing by the molar mass. Then we convert from the moles of iodine to the moles of nitrogen triiodide using our formula ratio. Then we convert from the moles of nitrogen triiodide to the grams of nitrogen triiodide using the molar mass. And that gives us the final mass of nitrogen triiodide.
Professor, I'm a little bit confused on what the difference is between that example and the previous example of that you showed us a little bit earlier. Not the last one, but the one before that. Oh, wait, it's the last one, I'm sorry. The mass of C2H2 contains 4.0 moles.
So
What was
the only difference is that this last step where we're going from the moles of one element to the moles of a compound to the mass of a compound. We've done that here. That's these last three conversions.
Mm-hmm.
The only thing that's new about this problem is that we're starting off by having to convert from the grams of our element to the moles. That's the only thing that's new in this example.
Oh, okay, I see.
Does that make sense?
Yes.
Perfect. Any other questions on this example? Okay, so let's talk about this second example where we're asked to calculate the moles of sulfur in 32 grams of hydrogen sulfide. So we're trying to go from the grams of hydrogen sulfide to the moles of sulfur. And if we're given the mass of a compound and we want to calculate the moles of an element, what intermediate units are we going to go through?
Mole.
Yep. And more specifically, we're going to go through the units of moles of hydrogen sulfide. So now that we have our solution map established, let's try to execute. So we're given that we have 32 grams of hydrogen sulfide. So to go from grams of hydrogen sulfide to moles of hydrogen sulfide, we know in 1 mole of hydrogen sulfide, we can calculate its molar mass. So we have 1.00 gram per mole of hydrogen. And in turn, we have 2 moles of hydrogen. And we have 32 gram per mole of sulfur. And we know that we have 1 mole of sulfur in our formula. And that gives us 34 grams per mole of hydrogen sulfide. Now that we have our molar mass established, to go from the moles of hydrogen sulfide to the moles of sulfur, we're going to use our formula. So how many moles of sulfur do we have per mole of hydrogen sulfide? What's our mole to mole ratio? 1 to 1, exactly right. So punching this into our calculator, we get 0.94 moles of sulfur. Does that make sense to everyone? Any questions on this example?
When we calculate the molar mass, do we need to round it?
You'd retain as many digits as possible from your provided periodic table. I'll provide you a periodic table for all exams, and you'll use the atomic masses in the periodic table that I provide you. Does that make sense? So in general, you write as many digits as possible for your molar mass, but I'll give you a periodic table with the exact atomic masses I want you to use.
Okay.
Perfect. So let's take this one step further. And now that we've seen an example where we've worked through these problems together, I'd like us to take what we've learned and take the solutions that we've seen, and let's try to apply what we've learned to this summative example. So in this case, we're doing a multi-step conversion from grams to moles of molecules to moles of atoms to atoms. So in this case, we're asked to calculate the potassium ions in 3.0 grams of potassium phosphide. So we're starting off with the grams of potassium phosphide, and we're asked to calculate the potassium atoms. We calculate atoms from the moles of potassium, and we can get the moles of potassium, the moles of an element, from the moles of our compound. So see, even for multi-step conversions, if you work backwards, you can figure out your intermediate units and then figure out the conversion factors that get you from point A to point B. So now that I have my unit conversion map established, let's begin. I have 3.0 grams of potassium phosphide, and I'm trying to convert to the moles of potassium phosphide. So in 1 mole of potassium phosphide, I have how many grams? Well, that to me looks like a molar mass calculation. So potassium has a mass. What is the atomic mass of potassium? If we break open our periodic table,
30.97.
For potassium?
Oh, 39.10.
Perfect. So we have a molar mass of 39.10 gram per mole of potassium, and we see we have 3 potassium atoms. One thing that I'd like to draw your attention to is that if you write out your molar mass calculation, it's also a useful way of keeping track of the atoms of each element. So I always like when problem-solving processes can be reused. So just keep in mind we have 3 potassiums. For phosphorus, we have 30.97 gram per mole of phosphorus, and we have 1 phosphorus atom. So punching this into our calculator, that gives us a mass of 148.27 gram per mole of potassium phosphide. So I plug that in up here. Next, continuing on with this idea, we are asked to calculate from here the moles of potassium. So how many moles of potassium do I have per mole of potassium phosphide? How many potassiums? As we see in the chat, 3 moles of potassium. Exactly right. Next, to finish off this problem, to go from moles to atoms. So how many atoms of potassium are in 1 mole of potassium? What number do we use?
Avocado.
Yep, Avogadro's number, which is 6.02 times 10 to the 23rd atoms per mole, just like a dozen. So we punch this into our calculator. So we have 3.0 over 148.27 times 3 times 6.02 EE23. And that in turn gives us 3.65 times 10 to the 22nd potassium atoms that we then round to 2 sig figs, which is 3.7 times 10 to the 22nd potassium atoms. Does this make sense to everyone so far? Does everyone see how we've delivered all of these pieces? We've done all of these pieces in our earlier problems. We're just now putting them together to solve more complicated examples. Any questions on this? Any questions on this first example? Okay, so we've seen an example. Let's now apply what we've learned. In this case, we're asked to calculate the atoms of oxygen in 32 grams of phosphoric acid. Now, you may say, why are we doing all of these mass to atoms conversions? Well, where this will show up is, let's say you're trying to prepare a buffer solution. The exact amount of buffer you add depends on the formula of the buffer, the molar mass of the buffer, and ultimately, when you're preparing a buffer solution, you're doing a mass to mole conversion. It also shows up when you talk about formulations where you're trying to make an ionic solution. In that case, again, you're doing a mass to mole or mass to atom conversion. So we'll be using a lot of these conversions in later chapters that are more directly applied to the nursing and allied health fields. So working on these fundamentals will really pay off. So with that said, let's look at this example and let's take about 4 minutes and let's try to calculate the atoms of oxygen in 32 grams of phosphoric acid. And we'll discuss this example in about 4 minutes. And if you have any questions, don't be shy to ask them verbally or in the chat. And don't be shy to share your proposed solutions verbally or in the chat, so that way we can have a reasonable discussion. And we'll discuss in another 3.5 minutes. And it's great to see students sharing their responses in the chat. Let's continue working through these examples. And let's try to get a reasonable pool of responses from all of the students in the class that we have. And it's great to see a large pool of responses from different students in this class group. We'll keep working through this example and we'll discuss in about another minute to a minute and a half, just to give other students enough time to formulate their thoughts, write down their proposed solution, and then be ready to discuss and review this example. Okay, so let's talk about this example. So first case, we are given the grams of phosphoric acid, and we are asked to calculate the atoms of oxygen. Okay, we're going to get the atoms of oxygen from the moles of oxygen, and we can get the moles of oxygen. If we have the mass of our compound, we can get our moles of oxygen from the moles of our compound. So now that we have this unit conversion scheme set up, all we have to do is execute. So we have 32 grams of phosphoric acid. In our first step, we know in 1 mole of phosphoric acid, we have how many grams? Well, we can calculate the molar mass. So we have 1 gram per mole of hydrogen, and we have 3 hydrogens. We have 30.97 gram per mole of phosphorus, and we have 1 phosphorus. And we have 16.00 gram per mole of oxygen, and we have 4 oxygens. So punching this into our calculator, we have 1.00 times 3 plus 30.97 times 1 plus 16.00 times 4, and that gives us 97.97 gram per mole of phosphoric acid. Perfect. So we have this part set up. We're next trying to go from the moles of phosphoric acid to the moles of oxygen. And how many moles of oxygen do we have per mole of phosphoric acid? 4, exactly right. Does everyone see the 4 oxygens in the formula? Perfect. It's nice to see some
Yes.
confirmation in the chat. Wonderful. Next, we're asked to go from the moles of oxygen to the atoms of oxygen. And how many atoms are in a mole, just in general? How many atoms are in a mole? What number do we use?
Avogadro.
Yep, exactly right. There are 6.02 times 10 to the 23rd atoms of oxygen per mole of oxygen. So when we punch this into our calculator, we get 32 over 97.97 times 4 times 6.02 EE23, and that in turn gives us 7.865 times 10 to the 23rd, that we round to 7.9 times 10 to the 23rd atoms of oxygen. So even though this example would look daunting if we approached it at the start of this chapter, it seems that almost the majority of the class was able to successfully complete this problem following these step-by-step guides. Really, complicated examples in chemistry are just built from a bunch of small pieces put together. A mass to mole conversion, a mole to mole conversion, and an atom to mole conversion stuck together and are linked together to allow us to go from the grams of phosphoric acid to the atoms of oxygen in that sample. Does this example make sense? Or are there any questions that I can address, or any aspects of this problem that I can explain in more detail? It's great to see how, as we move through the examples, students are getting more efficient in tackling these problems. wonderful to see. So let's look at an example that is a little bit more complicated, and this is about as hard as it's going to get on an exam. In this case, I'm asking how many grams of nitrogen are there in a sample of ammonium nitrate containing 4 grams of hydrogen. So in this case, you're going to need your nomenclature really well understood, because you need to be able to write the formula to begin to approach this kind of mass-to-mass conversion. So would someone like to tell me, what is the formula of ammonium nitrate? Let's think about that for a moment, and let's try to recall and utilize our nomenclature skills. Practice makes perfect. So the more you utilize a skill, the more efficient you are in accessing and utilizing that skill in the future. So for ammonium nitrate, we have a proposal of NH4NO3. Ammonium nitrate is a textbook ionic compound. Ammonium is NH4 plus. Nitrate is NO3 minus. We cross our charges, and that gives us NH4NO3. So now that we have the formula, we can think about how to execute on this problem. So we know that we have 4 grams of hydrogen, and we're trying to calculate the grams of nitrogen in our sample. How do we relate the quantities of 2 different elements, or the quantities of 2 different chemical species? What units are we? Moles, exactly. So we're going to go from grams of hydrogen to moles of hydrogen, and moles of hydrogen to moles of nitrogen. So now that we have our unit conversion scheme established, we're going to execute. So for 4 grams of hydrogen, we know that in 1 mole of hydrogen, we have 1.00 grams of hydrogen. In terms of moles of nitrogen per mole of hydrogen, looking at the formula for ammonium nitrate, how many moles of nitrogen do we have in the formula? How many nitrogen do you see? 2, exactly right. And how many hydrogens do we see?
4.
4. So we have 2 moles of nitrogen per 4 moles of hydrogen in ammonium nitrate. Now we're going to convert from the moles of nitrogen to the grams of nitrogen. And how many grams of nitrogen are present in 1 mole of nitrogen?
14.01.
Yep, exactly right. So we punch this into our calculator. So we take 4 times 2 divided by 4 times 14.01. And that gives us 28.02 grams of hydrogen, that because we have 1 sig fig, we just round to 30 grams of hydrogen. Oh, whoops, this is nitrogen. So we have 30 grams of nitrogen as our final answer. Does this make sense to everyone? Any questions on this example? Okay, so let's try to apply and work on one of these examples where we're asked to generate the formula before we complete our unit conversion. So, looking at the following example, we're asked to calculate how many grams of chlorine are in a sample of chlorous acid that has 16 grams of oxygen. Now, before I let everyone loose on this problem, would everyone like to help me out here and provide me what is the formula of chlorous acid? What is the formula?
HClO2.
HClO2, exactly right. Chlorous acid, OUS, is derived from chlorite, which has the formula of ClO2 minus. Crossing our charges for H plus and ClO2 minus gives us our final formula of HClO2. Okay, so we have our formula established. Now I'd like everyone to take about 3 to 4 minutes and complete this unit conversion now that we have the formula. If you're stuck on the formula, please go back and review your nomenclature notes. So the formula, it's not like it's in a table. The formula for chlorous acid is obtained from the nomenclature rules for polyatomic acids. So the OUS ending is derived from ions with the name ending ITE. So chlorous is derived from chlorite. We get the formula of chlorite from our polyatomic ion table. And then once we have the ion formula in charge, we cross it with H plus to get the formula for our acid. Did that answer your question on how you find the formula? Perfect. I know it takes a few steps, and we have examples of this in the chapter 3 notes and the chapter 3 recordings. So let's keep working through this example. If you have any questions or if you have any proposed responses, don't be shy to type them in the chat or to share them verbally. And I'd be happy to answer any questions that you have and provide feedback on your proposed responses. And we'll discuss this example in about 2.5 to 3 minutes. And if you're stuck on any part of this problem, don't be shy to ask a question in the chat or verbally. And we'll discuss this example in about another 2.5 to 3 minutes. And it's great to see that we have a pool of responses in the chat. Let's keep working on this example and we'll discuss this problem momentarily. It's great to see that we have a diverse range of responses in the chat. And let's continue to share our answers and we'll discuss in about another minute. Okay, so let's discuss this example. So in this case, we're given the grams of oxygen and we're asked to calculate the grams of chlorine in our sample. So how do we convert between the mass of two different elements in a sample? What units are we going to go through? Moles, exactly. So we're going to go from the grams of oxygen to the moles of oxygen, and the moles of oxygen to the moles of chlorine. So now that we have this unit conversion scheme established, let's now execute on this. If we have 16 grams of oxygen, we have 16 grams of oxygen. In 1 mole of oxygen, we know that we have 16.00 grams. Next, using our unit conversion factor from our formula, how many moles of chlorine do we have per how many moles of oxygen? What is our mole to mole ratio? 1 to 2. We have 1 mole of chlorine per 2 moles of oxygen. Finally, we're going to convert from the moles of chlorine to the grams of chlorine, and we know we have 35.45 grams of chlorine in every mole of chlorine. So punching this into our calculator, so we have 16 over 16 divided by 2 times 35.45, and that in turn gives us 17.725 grams of chlorine that we round to 18 grams of chlorine, respecting that we started with 2 significant figures. Does this example make sense? Any questions on this example?
Professor, where do you get the 35.45 grams of chlorine?
This is from the periodic table. So all of the atomic masses, the masses of an individual element, are found in the periodic table below the atomic symbol.
Okay, got it. Thank you.
Perfect. Any other questions I can address? You will always be given a periodic table for these problems. So always make sure you have a periodic table handy. If you have your book and you open up the cover of your book, it should be on the inside cover of your book. Your textbook definitely has a periodic table, and there's also a copy in the notes. And that's really important. You always want to have all of the information that you're able to access at your disposal. Very good question. If there aren't any other questions on this example, let's keep moving forward now and let's do another conversion relating to nomenclature. This time we're asked to calculate the atoms of sodium in a sample of sodium cyanide that has 4.5 grams of carbon. Now, just like before, I'm going to need us as a class to come together and find a reasonable formula for sodium cyanide. Would someone like to propose a formula for sodium cyanide?
NaCN.
Yep, exactly right. This is an ionic compound. Sodium is sodium plus, cyanide is Cn minus. We cross our charges, and that gives us a formula of NaCN. So now that we have our formula established, I'd like everyone to take a moment and complete the following unit conversion. This time we're figuring out the atoms of sodium given the grams of carbon. So let's take about 4 minutes to work through this example, and then we'll discuss momentarily. And as always, don't be shy to share your proposed response verbally or in the chat. And if you have any questions, really don't be shy to ask, either via public chat, private chat, or verbally. You can also send me a picture of your work or share your work using the annotate feature, and I'd be happy to provide feedback. I really do take all of the information in mind, in consideration, as we're working through these problems, as it structures what parts of the solution I need to emphasize and any questions I can explicitly address as I talk about the solution and as I talk about the problem. So let's keep working on this example, and don't be shy to contribute your responses to our class discussion or your thoughts on this problem to the class discussion. If something seems odd to you, or if you have an approach that you think would be reasonable, or a solution map, don't be shy to share that as well. And it's great to see that we have students sharing their responses in the chat. And we'll talk about this example in about another 3 minutes. And it's wonderful to see the development of students throughout this chapter as they are slowly beginning to tackle more and more complicated examples and becoming more efficient in solving these problems. And I really want to make sure I'm giving everyone enough time. So if you're working on these problems and you need more time, don't be shy to let me know. There's no problem with that whatsoever. These problem-solving sessions are designed for students to work through and sort of really struggle with engaging with the content, as that often makes and reveals questions that should be asked and then can be addressed in these lectures. So we'll discuss this example in about another 2 minutes, and if you need more time, don't be shy to message me. You can also send a private message via Zoom chat, and I do make sure to read all the messages that I receive during these lecture sessions. And again, don't be shy to share your questions and proposed responses in the chat. and we'll discuss in about another minute to a minute and a half. And it's great to see that we have a large pool of the class responding in the chat and verbally. It's great to see students engaging with the material, and we'll discuss this example in another minute. Okay, so we're starting off with the grams of carbon, and we're asked to calculate the atoms of sodium. We calculate the atoms of sodium from the moles of sodium, and we get the moles of sodium from the moles of carbon. So now that we have our scheme established, starting off with 4.5 grams of carbon, if we're calculating the moles of carbon, we know in 1 mole of carbon, we have 12.01 grams of carbon. This is our atomic mass or molar mass obtained from the periodic table. To go from the moles of carbon to the moles of sodium, we're going to need our formula. And in our formula, how many moles of sodium do we have per mole of carbon? We have a 1-to-1 ratio. We have 1 mole of sodium per 1 mole of carbon, exactly right. And then finally, to go from the moles of sodium to the atoms of sodium, how many atoms are present in a mole? What number do we use? How many atoms are in a mole?
6.02 times 10.
Yep, Avogadro's number, 6.02 times 10 to the 23rd. So to punch this into our calculator, we get 4.5 over 12.01 times 6.02 EE23, and that gives us 2.255 times 10 to the 23rd atoms of sodium that we round to 2.3 times 10 to the 23rd atoms of sodium. Now, with all of this established, a student asked me a question. Well, how do we get the formula? The formula is obtained using the rules in chapter 3. So sodium cyanide is an ionic compound. So sodium as a 1A element has a charge of +1. Cyanide is a polyatomic ion of the formula Cn-. Now that we have each of our ions, we cross the charges, and that gives us a 1-to-1 ratio, or NaCN. Does that make sense? This is repeated frequently in the chapter 3 notes. Does that make sense, how we calculated and how we figured out the formula? In terms of setting up your solution map, so we know from the problem what we're asked to calculate. So we're asked to calculate the atoms of sodium, and we're given the grams of carbon. Now, we know that we calculate the atoms from the moles. We always can get atoms from moles. So we can trace one step back, and we can get our atoms of sodium from the moles of sodium. Now, if we're given the amount of carbon in our sample, the only way that we can really easily right now relate the amount of one element to another element is using a mole-to-mole ratio. So in order to relate the amount of carbon and sodium in our sample, we're going to need to convert to moles. So that's why we went from moles of sodium to moles of carbon. And if we're given the mass of carbon, we can calculate the moles. Does that logic make sense? Does that backtracking logic make sense? Does that, no problem. The more practice we do on these examples, the easier it will be in terms of setting up these solution maps. And I find if you have the correct solution map, then the rest of the problem becomes very, very straightforward after that point. Then you're just plugging in your conversion factors.
Professor, on this particular problem, can you go over how we got the 2.255? Like, I know that the 12.01 is the mass of the carbon, but
Yes,
we multiplied those two.
Let,
We multiply we multiply the 4.5
yes.
and the 12.01.
What I'm going to do is let me actually share my screen. Let me share a projection,
Okay.
and from there I can show you on the calculator.
Okay, sounds good.
Okay, so here's what I'm going to do. Okay, so I have my calculator. I'm going to enter 4.5. Now I'm going to hit the division symbol, and I'm going to enter 12.01. I should get this number after my first input. Does that make sense so far?
Yes.
Then, since the entry in red is, since the entry in red is, since the entry in red is just 1, I don't have to worry about it. I mean, I can multiply by 1 just for completeness. Now what I'm going to do is I'm going to multiply by Avogadro's number. So I'm going to hit the multiplication symbol and then enter 6.02. And then I'm going to hit the EE button. Do you notice how this little power appears?
Yes.
And now I'm going to enter 23. And that gives me my final answer of 2.25 times 10 to the 23rd.
Got it.
Does that make sense?
Yes, it's just the 1 threw me off. I didn't know what you did there, but okay.
If
makes
it's
sense.
1, you can just ignore it.
Just skip that step.
Mhm.
Okay, thank you.
Yes, no problem. So this seems like a good stopping point for today. We'll continue on with chapter 4 on Wednesday. And for Wednesday, we won't have a new lab on Wednesday, but I am planning on lecturing. We're going to use that lab period to catch up on lecture, and that way make sure we're on track to finish all the chapters that we need to by the end of the class. Everyone's been doing great so far, and I really appreciate the students attending the lecture sessions. As I'll talk about in an announcement, the lectures are clearly paying off in terms of student performance. So keep attending lecture, even if it doesn't necessarily feel each day like the improvement is showing. I can see the improvement very clearly in your exams, lab reports, homework, and quizzes. It is making a difference. So keep up the attendance, and I really appreciate everyone contributing their questions and voices to our discussion. So with that said, I'm going to end today's lecture recording. Are there any last